The afternoon is going to be quite exciting. Now we have the introductory stuff behind us. True, some of it may have, it's a lot of new information. Some of it takes a little while to get used to. But you'll get there. And we will come back to many of the issues as we go forward, come back to many of the basic issues embedded in more interesting situations. So here's one general question we have. How do you model nonlinear growth? Growth that doesn't look linear, but has some kind of interesting twists and turns to it, like the loneliness of the twins, or like achievement growth that suddenly accelerates, or perhaps more likely decelerates, like it does in 12th grade in US school for math. But here you have a couple of ways. We counted 6 ways when we thought about it. You can estimate time scores, and we're going to talk about that quite a lot. We can have a more general growth model, adding quadratic or cubic growth factors to the linear. We can work with fixed but still nonlinear time scores. We can do so-called piecewise growth modeling, which becomes very popular. We can work with time-varying covariates because they also influence the growth, as we will see. Or models that we currently don't handle, namely models that are nonlinear in the random effects. So nonlinear function of these etas, e to the power of eta, for instance, is something that we don't handle. But before that, we want to have a word from our sponsor. Or did he leave? Nick? All right, he'll be back. And the first thing we want to do is then bullet number 1. Estimated time scores. No.
You're supposed to do the overview, then I do this.
Yeah.
Oh,
that was the overview. Linda was parking herself here very conveniently.
A long winter's nap. Oh, well. No rest for the wicked. Okay. So we're going to go through these various ways of doing nonlinear growth, and we're going to start with specifying time scores with using estimated time scores. Now, in the linear model that we looked at earlier, our time scores were all fixed at values 0, 1, 2, and 3. And now we're going to take a look at models like we see. Actually, I'll come over here for a change, since we now have both screens usable. So now we're going to take a look at some models that look like the 2 graphs here, where we have our time on the x-axis and our outcome on the y. And from time 1 to 2, the slope is steeper than from 2 to 3, and then 3 to 4 levels off a little bit more. So we don't have that straight line that's going to fit the means that are represented here. Or to the right in this picture, perhaps it starts going up, and then all of a sudden accelerates the development. And in these 2 situations, we have a time score of 0 and 1, and then 2 estimated time scores. So a fixed time score at time 1, a fixed time score at time 2, but at times 3 and 4, we allow the time score to be estimated rather than to fix it to a value. And the same thing on the right-hand picture. Now, when you have a growth model with nonlinear development with estimated time scores, you need 2 latent variables. You need the intercept growth factor and the slope growth factor. So those are the 2 latent variables, the 2 growth factors. Now, how do we actually specify this in Mplus? Well, all we have to do is, oh wait, one other thing different. So in Mplus, we're going to be looking at an example where we have grades 7, 8, 9, 10, 11, and 12. So that's one thing. So we're changing the data a little bit. and we don't have a picture of that, but it looks nonlinear, and it looks like there is a decrease, that there's not an increase between the scores in 11th and 12th grade, that it sort of flattens out. And this is, I think, sort of an effect that's seen between grades 11 and 12 in math. So what do we do to indicate that we want a free time score? We use the asterisk. That represents the freeing of a parameter. You can say nothing or an asterisk if you want to give a starting value. And what we're doing here is giving a starting value of 5. So our time scores are fixed at 0, fixed at 1, fixed at 2, fixed at 3, fixed at 4, and a free time score to be estimated with a starting value of 5. So that's what the language here means. Now on this screen, we take a look at we have our test of model fit. That everything looks pretty good. You know, that it looks like that model with the free time score fits pretty well. But let's take a look at the results and see what happens when we have a free time score. So here for I, now we're using the language with the bar, so we have a bar here instead of by. We see that the intercept slope growth factor has all of the factor loadings at 1. And for the slope growth factor, we have fixed at 1 for math 7, fixed, or 0 for math 7, 1 for math 8, 2 for math 9, and 10 for math, or 3 for math 10. And then let me put the next part over here. Yeah, no, I know. It feels good to walk across the stage just for exercise. Okay, and then for math 11 and 12, math 11 is fixed at 4, and we know they're fixed because we have 0 standard errors and 9 9/9s. But now, for math 12, it's a free time score. It's estimated. It has a standard error. It has a test of whether it's significant. And so it's 4.095. Now, the test of it's significant means that 4.095 is significantly different from 0. But what we're really interested in is 4.095 significantly different from 4. So is there a significant difference between that change from 4 to 4.095? And the way that we can figure this out is taking the difference here between 4 and 4.095 and dividing it by the standard error 0.042. And we'll see if we do that, that it's not significant, that change. So basically, it allows us, the estimated time score allows us to capture and better fit the data, by capturing the fact that the math score does not change significantly between 11th and 12th grades. Okay. Now, when we have a growth model, so that's to give you a little example of what we would be doing, there are some issues we have to think about. And one of them is for the model to be identified. So we need at least 2 fixed time scores, one fixed to a non-zero number, usually 1, in addition to the time score that's fixed at 0, the centering point. So we need a 0 and a 1 at a minimum fixed, and then some free time scores. And this changes the interpretation of the slope growth factor. So we can't interpret the mean of the slope as a constant for a change over all the time points anymore. We can only do that as the rate of change for a time score of 1. So from 0 to 1, 1 to 2, but not 2 to an estimated time score. Usually we fix the time score following the centering point at 1, but that doesn't have to be done. And I will show you an example of that here. So we know that the slope growth factor is the expected change in the outcome variable for a 1-unit change in the time score. And in nonlinear growth models, the time score should be chosen so that a 1-unit change occurs between time points of substantive interest. So for example, if you have 4 time scores, or 4 time points representing grades 7, 8, 9, and 10. If we give time scores 0, 1, free, free, so we're meeting the conditions of 1 being 0 to define the intercept growth factor and 1 being 1, the other 2 free. Then the slope factor mean refers to the expected change between grades 7 and 8. But if we instead take time scores of 0, free, free, 1, then the slope growth factor mean refers to the expected change between grades 7 and 10. So the linear part is between 7 and 10, and the other time scores are estimated. They may be higher, they may be lower, but they're not estimated on that line between 0 and 1. So if you choose to use free time scores, which is a good way of capturing acceleration or deceleration, just remember that when you interpret the slope growth factor, you need to keep in mind that it doesn't apply over all time points. Only the time points, like if you had 0, 1, well, no, that wouldn't work. But it only between the 0 and 1 here is that going to apply. It doesn't apply between time 1 and 2 and 2 and 3 and 3 and 4, just between 0 and 4, which makes sense. And then, like I showed you, when you estimate the time score, you can see if it's different from the previous time score, or whether maybe you didn't need that. You could fix it. Wait. Okay, so that's one way of dealing with nonlinear growth. A second way is estimating a quadratic model. So here we have a quadratic model. So we have our outcome is equal to our intercept growth factor plus our linear growth factor times x, the time scores, plus our quadratic growth factor times the time scores squared, plus a residual. Or you could center the time scores, as is shown in the equation below, where c is the centering constant, for example, x bar. And that can sometimes be helpful if you're having trouble estimating a quadratic growth model, because the linear and quadratic growth factors are sometimes highly correlated with each other. So here's our, we need 3 latent variables when we have a quadratic growth model: intercept, linear slope, and quadratic slope. So here's a picture of what we might have going up at time 1 and time 2, coming down time 3 and time 4. So you can imagine that we're going to have more parameters to estimate because we have 3 growth factors now, and that third one's going to have a mean and a variance, and it's going to have a covariance with the other 2. So that implies that you have to have more measurement occasions to identify a quadratic growth model. So here we have our linear slope is time scores are 0, 1, 2, and 3. And it's very simple to create the time scores for the quadratic growth factor. You just square the linear growth factor time scores. So 0, 1, 4, and 9. So in our growth modeling language, for a quadratic model, you just give 3 names, and we always use IS and Q, but you don't have to. You can use whatever name you want, that is falls into the variable name requirements. So since we have 3, Mplus knows, okay, it's a quadratic model because it has 3 growth factors. So if you give the linear time scores of 0, 1, 2, and 3, then Mplus does everything else behind the scenes and creates the squared time scores for the quadratic factor. Or you could specify this by using the by statements, where the intercept growth factor loadings are 1, the slope growth factor, linear slope are 0, 1, 2, and 3, and the quadratic slope growth factor loadings are 0, 1, 4, and 9. And you can also do this for a cubic model by giving 4 names before the bar, and an intercept-only model by just giving 1 name. So the bar statement makes a decision about what kind of growth model it is by how many names it finds before the bar statement. Okay. Now we're on to the third way that you could model nonlinear growth. And that's using fixed time scores that fix the time scores at the shape that you're interested in. So you need 2 latent variables when you're describing nonlinear growth model in this way: intercept and slope. So let's say we have something and we know that it develops according to a logarithmic curve. So what we do is we figure out our time scores by taking the log of time. So time is 1, 2, 3, 4. We take the log of 1, 2, 3, 4, and we get time scores of 0, 0.69, 1.10, and 1.39. So you would say, let's say it was math 7 at 0, math 8 at 0.69, math 9 at 1.10, and math 10 at 1.39. So that's how you would use a curve, a known mathematical curve, to estimate a model and see how well that fits your data. No, we're just coming to that. Isn't this head circumference? Yeah, okay. All right, so here's, wait, is that really true? Yes. Okay, so one example, as I'm being prompted, is that this could be used for head circumference. So did you try that one?
There's a nomogram for head circumference.
No, but I mean, you were saying you hadn't found a good model.
I haven't tried it.
You haven't? Shame. Okay. So here's another example, an exponential curve. So once again, you exponentiate time minus 1 and then minus 1 to get the time scores. And if you do that, you get time scores of 0, 1.72, 6.39, and 19.09. So, the world is open to you to find a curve that matches your growth, and you can use this to do that. Now, a fourth way of attacking nonlinear growth is piecewise growth modeling. I think I'll put that over here. So in piecewise growth modeling, you use different pieces of the growth model to represent different phases of development. So let's say you have a situation where you have slow growth, and then at a certain point, it goes at an accelerated rate. So you can use different pieces for different parts of development, and that helps capture this nonlinearity that we see. Each piece has its own growth factors, and therefore each piece can have its own coefficients for the covariates. So this is an interesting model because it may be that the slower growth is predicted by different covariates than the more accelerated growth. And you can actually model, in this model, you can actually get at that kind of information. So in the situation that I'm showing here, we would have 1 intercept growth factor and 2 slope growth factors. And the first piece would be the first 3 occasions, and the last piece is 3, 4, 5, and 6. And you develop your time scores just to match this. So let's say you think you have linear growth here. So for the first part of the model, S1, the slope growth factor, your time scores would be 0, 1, 2. And then you just continue with 2s the rest of the way. For the second part, it starts at 3. So it was all zeros up to the third, and then 1, 2, 3. And that would represent the growth for this part of the model. So this can be a useful model if you have something that breaks at a particular point like that. Now, you can also use a model like this, which I consider more of a sequential process model, but it is in two pieces. And the reason I consider it more sequential than a piecewise is that you have two intercept growth factors. So you have an intercept growth factor here and a slope, and then this part of the model has a different intercept growth factor, whereas in this model on the left, we had the same intercept growth factor and two different slope growth factors. So here we would have two intercept growth factors, as I just said, and two slope. So the first slope would be 0, 1, 2, and then the other one 0, 1, 2. So you would set this up as a sequential model. But these are two things you could think about if you have this type of nonlinear growth. Now we're going to take a look at a nonlinear growth model for the Math 7 through Math 12. Put that over here. That we talked about earlier, where we let the time score be free. So how would we set that up? So we said that we would have one intercept growth factor for a piecewise and two slope growth factors. So you can see here, by looking at the time scores, 0, 1, 2, 3, 3, 3, that Math 7 through 10 is the first piece of the model. And then Math 10, 11, and 12 is the second piece, because our time scores are 0, 0, 0, 0, 1, 2. So we have 7 through 10, 10 through 12. Those are the two pieces of the model. And we can regress all three growth factors on the three covariates we talked about earlier: female, mothers, education, and home resources. Excuse me. And then we get our tested model fit, which looks okay. Once again, with chi-square probably sensitivity due to the large sample size. But what's interesting about this is what I said earlier, is that the intercept and the two slope growth factors can have different predictors. Different predictors can be significant. And we see that they're all significant, again, for the intercept growth factor, as we saw earlier. But for the two parts of the growth, the first part, 7 through 10, which we looked at earlier, mother's education and home resources, are significant. But for the third part, between grades 10 to 12, none of the covariates are significant. So you can see there's that difference in what predicts which part of the development of math. So grades 7 through 10, the kids are younger, they're probably more affected by mother's education, home resources. By the time they get in grades 10 through 12, they're much more independent of the home and having many more experiences beyond just the home. So that could account for the fact that those aren't as important anymore. So that's the idea of what you would get if you did this kind of modeling, and how it might help you understand your data better. So there are some examples or some suggestions for nonlinear growth. Citrus?
All right, how are you feeling? Anybody yawning? Well, we'll try to spice it up a little bit with, now you're ready for intermediate growth models. So now we're going to cover all kinds of exciting topics. And the first one is individually varying times of observations, and actually packaged together with random slopes for time-varying covariates. which, if you remember, were the two features that set general growth modeling apart from SEM. Things that cannot be done in a mean covariance structure SEM framework. And we're going to talk now in terms, notation that comes straight out of the HLM literature, Raudenbusch and Bragg's book. And in this area, you have to get used to working with many different kinds of notational systems. Here is another one that they use. Y is still Y, but X is no longer X, but A1. Maybe it's A placed on H, I don't know. So you see A1 sitting down here, and instead of etas, or I and S, we're now going to work with pi 0 and pi 1. So this is I and S multiplying X, which is now A1. And we're going to introduce a time-varying covariate, A2, for instance, math course taking, and it sits out here in equation 55, the pi 2 times A2 term, where pi 2 also has subscript I, so varying across individuals, plus it has subscript T varying across time as well. And X is the time invariant covariate, so that's what we used to call W, and it sits down here in equation 56 on level 2, where the three random effects variables, pi naught, pi 1, pi 2, are linearly regressed on X with intercept and slope and a residual that the multi-level text calls R. And all of those three R's can be correlated. That model is dealt with in the following way in Mplus. Here is how you can visualize it. If you don't like formulas but like drawings, then you look on the right screen. If you don't like drawings and like formulas, you look at the left screen. So now I'm looking at you and I can tell who's who here. You look cross-eyed. Anyway, so you have the model here. You have the outcomes. You have I and S, growth factors. And you have time invariant covariates, female, mother's education, home resources that Linda worked with. Now here you have the time varying covariate, course taking, math course taking in grades 7, 8, 9, 10. You have the definition of that in the typical basic run on LSA that we talked about before lunch. But it has to do with how advanced the math course is, if it has to do with algebra, geometry, or whatever. And the influence of the time-varying covariates onto the outcomes now has a random slope sitting here. And that is the pi 2 I, pi 2 sub I, which we have renamed. We don't like the pi 2, so we call it STVC, slope for a time-varying covariate, to make it a little bit more humanized. And to keep working with the latent variables, circles that is, for latent variables, STVC is a latent variable, that is pi 2 is a latent variable because we don't see it and it varies across I. And to keep that notation, we're doing these broken arrows style of drawing, assigning that latent variable to sit as a multiplier on each of these paths. It is the slope for these paths. How much does course taking influence math achievement is determined by STVC. The only thing being that that slope varies across individuals. So a given amount of course taking may influence the achievement differently for different individuals. So different individuals benefit differently from the same amount of course taking is what this model says for all time points. So that is an interesting model, as we will see when we talk about the interpretation here in a second. How do we do it in Mplus? Oh, here you have it on this slide 130. course taking, highest math course taken during each grade, pre-algebra, algebra, geometry, algebra, pre-calculus. This is sort of a continuous variable then, going from 0 to 3, 0 to 9, I guess. And anyway, so here you have then a new, excuse me, new option in Mplus, the centering, and another new option, t-scores. So centering is now of the simple kind. It doesn't have to do with the time centering, but it has to do with the covariates. Grand mean implying that for each covariate, we're going to subtract the sample average. We subtract the sample average so that each covariate will have mean in the sample of 0. And that's going to make some things, some interpretations easier. More to the point, though, we're going to work with time scores here. And those are the ones that go together with that keyword at. We're going to read in the data. If you look up here in the variable command, we have data A7 through A10. Those are the four variables that sit in the data, and that can potentially, A7 then can potentially vary across people, across the rows in that data matrix. And those are the what we called X's before, time scores, now read in as data instead of being dealt with as parameters. So time scores, those variables are designated as time scores. And we're going to put those, use those time scores in the model using the at option. So here is a, on slide 131, is a growth model for linear growth where math 7 through math 10 are measured at time points, time values A7 through A10. That gives a possibility of these time scores varying across people for a given occasion of measurement. To be able to use that at command, you have to use, I believe, type equals random for that reason alone. So in the analysis type, we now have to add the word random. When Linda went over, well, let me back off of that for a second. And so here's one of the two features. Individually varying times of observations captured by this expression here, IS bar math 7 through 10 at A7 through A10, where A7 through A10 have been defined as t-score variables. And the second issue was that we have random effects for time-varying covariates, the STVC, on slide 129. STVC, the random slope for the effect of course taking, it is defined by a bar statement as well. It says that when we regress math 7, say, on course taking at grade 7, during grade 7, that slope is not fixed, but it is random. So we give that random slope the name STVC. So if you didn't say STVC bar here, then that would be a regular fixed slope. No variance for it. But when we say the bar, it is a random variable with a mean and a variance, and a variable that can be related to other variables. And we're going to define that STVC for each of the 4 time points. And in this case, you see that we're using the same STVC for all 4 time points. We could have used STVC 1, 2, 3, 4. If we had done that, if we had STVC 1, 2, 3, 4, then we would have accommodated the subscript t for pi 2, in addition to having accommodated I. But now, the way we've written it, we have dropped I. We're saying that that random effect is the same across the time points. So the variation in, the individual variation in impact of course taking is the same across these grades, is what we're saying. Also, from a practical point of view, it's a little harder to identify and estimate the model that makes the slope of the time-varying covariate vary across individuals and time. And then we have I and S on the background variables, and we also have STVC on the background variables. So STVC, looking at the right screen, is regressed on female mothers' education and home resources, which is a very interesting idea because it says that home background influences how much you can absorb the course taking. So home background influences the size of this coefficient for a person, which influences how much course taking influences math achievement. It's an interesting indirect effect. Home background indirectly affects math through STVC. And, well, not an indirect. Well, maybe that's not what I should stress. Maybe I should stress instead it's an interaction effect, right? It's an interaction effect. Female mothers' education and home resources interact with course taking in its influence on math achievement. It's sort of a, as it will come out, it comes out that the product of the background variables times the course taking. But I'm getting ahead of the story, so let's stay with it here now. So that's the input. Not very hard to do. And this is the case, though, where you don't get a chi-square test of model fit. And we'll tell you why in a second. But let's just live with it for now. You do, however, have your log likelihood. And then you remember what I said before lunch, that two models can be compared if they're nested by a likelihood ratio chi-square test if you consider 2 times the log likelihood difference. 2 times the log likelihood difference is a chi-square test under certain assumptions with degrees of freedom equal to the difference in number of parameters of the 2 models. So here you have it. I even have this Bayesian information criterion, BIC, which we're going to use a lot in August. But this is March, so it's a little early to use it. But it could be used. And here then we have the results. I on the background, S on the background, STVC on the background. And lo and behold here, I think Linda found that earlier that S on the home background was significantly influenced by mother's education and home research, I believe. Right, Linda? Yeah, she says yeah. I was just testing if you were asleep. But now it's not significant anymore, because now we have a more general model here with time-varying covariates. Oh, wait, I'm looking at the wrong column. Yeah, you were going to say, right? But there was some protest there. They weren't asleep. I was asleep. So here, so here's the excitement. I think we didn't have female. The female significance here is now coming out, looking more like the picture we showed this morning. But we still don't know if it's real because this is just our feeble attempt at bringing in some rudimentary covariates. So the truth is still out there to be sought after. STVC, what's that related to? Home resources. So the more home resources you have, the higher the STVC. The higher the STVC, the more course taking influences math. So home resources interact with course taking to produce good math achievement. That makes sense, right? So you take a lot of difficult courses at school, and then you come home and your parents explain it to you. And do your homework. But it's sort of an interesting interaction that these multi-level models. This is a multi-level model that you're looking at, right? It's just that Mplus is just one level, but it's multi-level repetitions across time. I mean, different time points and on level 1 and different individuals on level 2. And we have also significant covariance between the STVC and I and S, which sits in these double-headed arrows here in the figure on the right. So that's kind of interesting. So we illustrated 2 things here. Oh, and you have an intercept also for STVC. STVC intercept is positive. Now, we don't know what the mean is, but now you are so into it that you know immediately that the mean of STVC is the intercept of STVC plus these coefficients in its regression of the covariates times the sample mean of those variables. And I'll just tell you that that total mean of STVC is positive. So on the whole, it pays to take advanced math courses. Trust me. You're experiencing it right now. Anyway, and it seems to be a healthy variation in STVC. The standard errors are small relative to the point estimate. Once again, note that STVC is a dependent variable. Therefore, we're talking about a residual variance, saying there is much more that can be explained in the STVC variation than is accomplished by those three time-invariant covariates. So again, going back to this, slide 127, we illustrated two things at the same time: random slopes for time-varying covariates and individually varying times of observations. They don't have anything to do with each other, but we just wanted to put it into one example. Note further that in this example, the first issue was totally irrelevant because there is no variation in the time score. Everybody who's in grade 8 is in grade 8. So there was no individually varying times of observation. It would have been if you somehow took into account that people were held back in grades and differed in ages, something of that sort. But anyway, at least we showed how to do it when you need it. So here's the question, and on slide 135. Why no chi-square? Sounds like our 6-year-old grandson talking. Why no chi-square? Why is there no chi-square with random slopes for random variables? Yeah, people coming from the SEM, CFA world, they really miss those chi-square model test of fit. But if you run any multi-level program like HLM or MLWin, you never see them. Which, you know, it's a blessing because they're usually bad, but they are depressing, but they nevertheless are of value. And they could be used for many, if not most, multi-level models. Why don't we see them? Well, consider as an example individually varying times of observation. So A1T is our old XT. But note here now that we have XTI, and it's the I that creates the individually varying times of observation. At the same measurement occasion, people are of different ages, for instance. And because of that, if you look at the variance given that time score, it's the variance of the intercept growth factor, the variance of the slope growth factor, times A squared plus a covariance term. But the fact that the variance changes as a function of the time scores means that there is not a constant sigma, constant population covariance matrix. There's not a constant covariance matrix for Y to test the model fit for. There's not one covariance matrix. So the mean and variance covariance matrix testing of SEM falls apart here. If you didn't have individually varying times of observations, and if you didn't have random effects for time-varying covariates, you are able to get a chi-square. So Mplus will give you a chi-square when you can get it. So for those models where you don't have these two features, and I would say that most growth models don't have them. So I think it's good that a program like Mplus can provide you with this chi-square test of fit, albeit perhaps depressing at times. So actually, Raudenbusch wrote a chapter on that in what was the best methods of analysis of change, and talked about how SEM couldn't be growth modeling for these reasons, that it couldn't handle these two complications. That doesn't mean, though, that it can't, that the latent variable modeling framework cannot be used for growth modeling, as we see here. Now, this I'm not going to go through. It's a little bit too technical and better spoken about at a different pace. Let me instead go to slide 137 and onwards. And here's a really exciting situation, which I don't think is stressed often enough. We have so far talked about two alternative models. The one on the left here is the first model we showed when I tried to just quickly make a distinction between time invariant and time varying covariates. The modeling here is done in a way that could be handled by the SCM, mean and covariance structure modeling framework. Why do I say that? Well, it's because we don't have individually varying times of observations, and we don't have random slopes for a time-varying covariate. We don't have a random slope for a time-varying covariate. Random times random, even if they're both normal, gives non-normal models, and they don't fit into the mean and covariance structure modeling framework. Anyway, so here the parameters are fixed. You estimate a slope, or perhaps you estimate a slope that varies across time. You can put it equal across time or different across time. On the right is the model that we just looked at. We have a random slope that varies across individuals. The way it's drawn here on the right is that it doesn't vary across across time, but it could vary across both people and time. But more commonly, in the multi-level framework, it varies across people, but is held equal across time. Whereas here, it doesn't vary across people, but it's possibly allowed to be different across time. Did it sound like I just said the same thing over and over again? I don't know if I did. Now, but these are not the only model alternatives here. Well, we talked about several others. For instance, course taking in grade 7 can influence not only Math 7, but Math 8. How much you took in grade 7 can benefit you throughout the grades, if you will. And that's quite easy to specify in this framework. Likewise, you could have here, you could have a slope for a time-varying covariate, which is random, influencing several time points. But I haven't seen that in the multi-level literature, and the multi-level literature would look at this as a two-level model where a distinction is not made between the different time points, typically, so that it's not that straightforward to allow for differences across time. But my main point here is that we want to go through these modeling exercises on the LSA data, on the math achievement data, and see where it brings us. So I'm going to do the first model, which is the one that was on the left. That's model M1. I'm going to do model M1. I'm redoing it under type equals random because that gives you a log likelihood in the same metric as we get when we do the random slope, model M2 random slope. And that was the technical background for that was given on the pages that I skipped. The log likelihood is in a different metric between these models unless for the more standard SEM-like model, you need to put type equals random there to get it in the right metric. Anyway, so you have this model that you recognize now. We go back to grades 7 to 10. It's very straightforward. Here is the influence of the time-varying covariates. And you note that there's no equality put here. They are four different slopes sitting on those lines over there on the left. 4 different slopes. And you get in this case, you get a chi-square test the model fit because there is no individually varying times of observations. There is no random effect for time-varying covariates. So you get a chi-square. You wish you didn't. because the p-value is low and the chi-square is very high relative to its degrees of freedom. And even though we use MLR here, apparently, a non-normality robust chi-square, that's when we get the asterisks here. Scaling correction factor for MLR, if it's very different from 1, if it's a lot greater than 1, that means we have very non-normal data, and we don't have non-normal data, so we can't blame the lack of fit on non-normality. Well, we will have to blame it on something else, like sample size. But we're going to modify this model. Here we continue. Even CFI is bad. This is a bad CFI value. You want it to be 0.96 or more, typically. Let's see. And here you have the results, I and S on. And then we're particularly interested in the effect of the time-varying covariates at the bottom of slide 143. And they are significant. So it helps to take math courses. That's nice to know. Throughout all of the grades, it helps. The slopes are similar at the different time points. If I go back one slide, 1.9, 0.9, 0.9, they're pretty similar across time. So differences across time, it was not that important to cover that. You can actually test that they're equal or not by doing a second run where you hold them equal, and then you have two nested models, and you can take 2 times the log likelihood difference to get a chi-square test of the equality of effects of the time-varying covariates onto the outcomes. Let's see, is there anything else of interest here? Not really. You have modification indices, which may point to some nonlinearity. Whenever you have math on S, for instance, then that could be that the time score is not right for that. The linear time score is not right. So it's a chi-square value of 16.8, which is a lot bigger than 3.84, the 5% critical value. On slide 147, we have something that's bolded, so that has to be important. Do you know why? Okay, no help there, says Linda. Okay, on statements, I on math course is 7. It's huge, folks. 582. What have we done wrong? Time's up. Well, we have neglected to let course taking in grade 7 point to I. This course taking in grade 7 is a concurrent event with I, right? We define I to be the initial status because the time score is 0 for the slope, which you see here by the absence of an arrow. The absence of an arrow says that the arrow slope is 0, which says that the time score x sub 1 is 0, which means that I is defined as the initial status, the systematic part of the variation of math achievement in grade 7. We're saying that that is uncorrelated with course taking in grade 7. So here your kid goes and studies math all up through grade 7, and at the end, in the spring of grade 7, it takes the math test, and we're saying that the systematic behavior part of that is unrelated to how much course taking they take. No wonder that the modification indices scream at us here, and it really says that this model is incorrectly drawn. At least course taking 7 should be perhaps seen as influencing I. Logically, that seems to be a reasonable way of doing it. And it says if we do that, chi-square is going to drop by 582 points. And that's pretty high. So that means when chi-square drops, the model fits the data better. Low chi-square, good model. And again, modification indices should not be followed blindly. For instance, here, the math performance in grade 9 seems to depend on course taken in grade 10. So don't take it too seriously. The courses you're going to take in grade 10 influence how well you do in grade 9. That's sort of ESP or interesting. So you have to think about what makes sense. Now, Model 1 then, here is the summary of stuff. Model 1 is the one we just talked about. And let's see, log likelihood 26,870. Was that the model with or without the direct effect? Where's the likelihood? Log likelihood 26,869. 26,869. 26,869. Yes, this is the model. This is the model that we found this potential misfit of course taking point into I. That effect, course taking into I, is not included here as far as I can tell. And you have 19 parameters. What about Model 2? What is Model 2? Well, Model 2 is described here. Random slope for the time-varying covariates. Same across grade. So the slope varies across people, but not across grade. So it is exactly like the drawing here for Model 2. And it has log likelihood minus 26,846. And then you have to know a high log likelihood is a good log likelihood. So 26,870 sits down. Here's 0, here's negative, and here's positive. Minus 26,870 sits down here. Minus 26,846 is up here. So this is better. This is better than that. So it's a higher log likelihood. And now you should then protest and say, well, of course, it's trivially true that the likelihood gets better for M2 because you're using 3 more parameters. And when you include more parameters, you're going to get a better fit to the data, better log likelihood. So therefore, you have to have an independent counsel here that evaluates the value of the model by weighting together the goodness of the likelihood with the parsimony of the model. So BIC will positively value high likelihoods, but negatively value a lot of parameters. BIC likes parsimony. So counterweighting those two things, weighting those two things against each other, you pick the BIC with the lowest value. This BIC is lower than that BIC. So you would choose M2 over M1 in this case. Why am I pointing to BIC here suddenly? I thought we were talking about chi-square difference testing. Well, these two models cannot be chi-square differenced. They are not nested. They are different. One has a random effect with the equal effect over time. The other has a fixed effect that's different across time. Those two models cannot be chi-square differenced. They're not nested, and therefore, for those kinds of models, BIC is very useful. Then you go with the lowest BIC. The only requirement for working with BIC for two different models is that you work with the same variables. Now, what is M3? What is M3 here? Well, M3 is M2, the random slope model, plus I and S regressed on TVCs. So now we're getting advanced. We're regressing I on TVCs. That's what we talked about. I regressed on course taken in 7. But apparently we're now bringing in S as well. So let's see the model diagram of that, because M3 looks promising, right? Its likelihood is even higher up. It's a smaller negative value, so it's higher up there. True, it has even more parameters, but the BIC is the lowest. The Bayesian information criterion is the lowest of all 3. So that will be the preferable model. So let's see what it looks like in the model diagram form. There's model M3. So let's look at it a little bit. And we see that course taking in grade 7 influences I. That was the left out path that we saw a very strong signal about the need to include that. But now we're also letting course taking in all grades influence the growth rate. Because growth rate is something that happens across the grades, whereas I is defined at grade 7, right? I is initial status. So it would be very strange if we let I be influenced by course taken in grade 8, 9, or 10. Not strange if it's influenced by course taken in grade 7, but initial status shouldn't be influenced by something that happens later, right? It doesn't make sense. So one could argue, I don't know if it's publishable, but one could argue that this is a reasonable model, logically or substantively, and it certainly is the better fitting model of the three. But this is just for you to have as an exercise of thinking about how to think about these models, and in particular how to deal with time-varying covariates. And you have the input for this model, model 3. Now you read this very rapidly. This is like a cheap novel. It goes very quickly. That's the growth model. Here's the random effects for time-varying covariates. And here we regress I, S, and STVC on the back, on the time-invariant covariates. And we regress I on math course taken in 7, and S on math course taken in 8 through 10. So you have the results here. Let's see what survives here. Well, it looks like Mother said home resources doesn't survive. Home resources is no longer significantly influencing STVC. So I'm sorry we lost that interesting substantive part of the story. But it's probably closer to the truth. Yeah. And with that, I will be quiet for a while. Yet another kind of time-varying covariate.
So I'll just do this.
Yeah, that's right. Good.
Okay, we're going to talk about another application, and that's time-varying covariates representing status change. So what we're going to be looking at is you can think of the Y outcome as heavy drinking. And you can think of the X, this is time, of course, and this is our growth model. And the time-varying covariate that we're talking about is being married or not. And I guess this is a known in the literature that getting married drops heavy drinking by an increment, a known increment, such that the entire growth curve moves downward, and that the earlier in time that this happens, the larger the drop. So what we're looking at here at X1 is this is the regular growth model, and for those who are married at this time point, their growth drops a larger increment and then is represented here. Later in time, being married drops it, but not quite as much, and even later in time, it drops the trajectory, but still not as much as it did. So the drop decreases over time, but it is a constant shift. So that's what we're saying when we say status change. So the status is going from unmarried to married. And this is a model that may or may not match what you're thinking about, or what your data situation. But let me just, well, actually, I think I'll put this on this screen and leave that there. Okay, so on the right screen here is how you would set this model up. Maybe I should put it on both screens so it's easier for everyone to see. So now it looks really complicated, but with everything you know so far about going from a picture to a diagram, you're going to recognize that this is just a growth model. So this part of the model is simply a growth model. So we have our alcohol use at time 1, time 2, time 3, and time 4. We have our alcohol use intercept growth factor, our alcohol use slope growth factor, intercept growth factor, slope growth factor, and then we have regressed the intercept and slope growth factors on a set of covariates: age, gender, Black, Hispanic, and education. So that's just exactly what we've been looking at. The status change part of the model is represented here with the circles and the squares in the bottom right part of the path diagram. And let's just look at this and think it through and think how we would do this. So we know the circles are latent variables. We see that the circles are pointing to, let's see what the first one points to. It points to time 1, time 2, time 3, and time 4. The second one points to time 2, time 3, and time 4. The third one to time 3 and to time 4. And the fourth one only to time 4. And you can look below and see that the relationship for the status variable. So the squares represent the status variable, or being married or not, changing to being married, this marital status. And the status variables point to these circles. So we know that this is like this on this. So these are regressions. These are all regressions, but when we have latent variables, we use the by statement. So basically, what you would add to the Mplus input language, and I'm going to go a little slowly because we didn't have a slide with this language. So for this part of the model, the input language is going to be F1 by, and it's going to be T1 or Y1 through Y4 at 1. So T1 by Y1 through Y4 at 4. The next one is going to be T1 by T2 rather, by Y2 through Y4 at 1. Then T3 by Y3 through Y4 at 1. And T4 by Y4 at 1. So just to kind of think about what we've learned today, so we're fixing them at, everything's fixed at 1. And what does that mean? That means an intercept growth factor. So what we're doing is we're creating intercept growth factors. Time 1 is related to all the time, or T1 is all of the time points, T2 the next 3, T3 the last 2, and T4 the last 1. And then we're going to relate those to the status variable, and that's going to lower the intercept for the people who have the status change. So it's going to affect the intercept growth factor for those people. So over here, then we regress T1 on, let's say it's S1. So let's say T1 on S1, T2 on S2, T3 on S3, and T4 on S4. So what we added, just to summarize, is we've added by statements creating additional intercept growth factors, so to speak, and on statements relating those growth factors to the status change variables. And if you note in the picture, in the path diagram, we don't have any residual arrows. So we would also have to add the statement T1 through T4 at 0. So that's to account for the fact that we're not estimating residuals, which we see in the model by no residual arrows. So when you do that, then you obtain status change values, means here, minus 29, for example. So that, for the people who have status variable at value 1, their intercept value is going to drop minus 0.29. So it just basically shifts the growth curve. It's a permanent shift in the growth intercept, rather, down. And it's for people who have marital status 1 at time 1, it shifts greater usually than the others. And you can see that it's minus 29 for time 1, minus 28 for time 2, and minus 20 for the last 3. So in the picture that I had showed you, let me just go back to that. These values represent this incremental change that we show here. So the values in between the factors and the status variables. So this is, if you have a situation where you have some status change variable like that you want to incorporate into your growth model, then the picture here shows you how you would do it. And then, as I said, we would have the by statements that reflect this part of the model, and the on statements that reflect this part of the model, and the fixing of the residuals to 0 reflected by no arrows, residual arrows going into the factors. That's that. Do you want? And so this will be the end of this section. So Bengt may want to add something, but then we'll just take questions and have our break.
Yeah, let me just emphasize one thing that I forgot to mention that could be of interest. I want to contrast these two models.
I forgot to do this. Should I do it after the break?
Yeah, you have time.
Okay. Sorry.
So we want to contrast these two approaches to time-varying covariates. On the left, on the right here, we have a status change, so that once this status change has happened, once this person has gotten married, they drop down and stay on another developmental path that's lower throughout. It's that constant change in one direction that's exemplified by those factors at the bottom of Linda's graph. Here, however, these effects, could you do 157? So you have those status changes here. You see that it's really, it looks like a lagged effect, that you have an effect on time 1, but also on time 2, 3, and 4. And it's the same effect, it's constant 1 here, that the intercept gets pulled down by, or it could be pulled up, but it's pulled down because it's a negative sign. Now here, over on the left, we have only a temporary change. Whatever the time-varying covariate is, it can increase, as in this case, increase math achievement, or it can decrease it at that time. And same thing for grade 8, and 9, and 10. It's not necessarily a constant or a permanent effect, it's a temporary effect. I think econometricians call it a temporary shock or something like that. So it's two different kinds of thoughts about time-varying covariates, depending on your type of application. So with that, I think we can take questions, and we're on schedule again for some reason.
Exactly. Wait, where's the place to stand?
Lady in the middle?
Yes, I was wondering on this time status changes on 127. So what if you got married and then divorced and then married? Are you?
Well, you'd be jumping around a lot.
Yeah. Now, so this is tailor-made for the situation where people get married at the same time. But then, of course, if they then get divorced again, you would have to have another potential status change variable in there when they get married and then they get divorced. They have to be two status change variables, more complex.
Yes.
So can you use, like, if you're modeling entry into school, like movement in and out of school over time,
Okay, so the question is, what if the time-varying covariate has to do with movement in and out of school? Is that school removal, do you mean?
I'm sorry.
Is that school has to do with school removal, that you're in school and then out of school?
You're out, like in college, people dropping out of college and then going back in.
Oh, okay. People dropping out of college and dropping back in. Well, folks, which model would you choose? It's a think piece for you.
So you would want to understand why they are doing that?
Or how it influences.
Understand how that affects like their career decisions, for example, moving in and out of school.
So, but the career would come after them dropping in and out of school?
Right. So like if you dropped out at time 1, then it might affect your time 2, 3, 4 in decision.
It would seem, well, it's a complicated question because it's sort of like, does all the school happen before you see how they do in their career? Or are they dropping in and out of school during the career process? So then you could have some sort of a parallel process type model, I guess. But I'm not sure that dropping in and out of college that way
Can I ask, do you have the same
developmental.
Do you have the same outcome over time that you're looking at? Same outcome, but they're just in school or out of school at different time points?
And what's the outcome? Like a
Decision about your career. How decided you are about your career.
How certain you are about your career is the outcome.
But do they have the career already?
No, it's like
It's sort of a projection of what they think they want to do. So if they're certain about what they want to do, it may be more motivating to be in school, for them to stay in school rather. Right. That's, I don't know, that nothing pops up.
Yeah, I would almost vote for the left screen rather than the right screen. But we may have, what is the group consensus here? Let's take a vote.
Model.
Can we reconcile you? Yes, somebody had a question.
on slide 147.
147?
Where you have the model qualification. You pointed out that one that has 588, but I was wondering about, for example, the one that has 475, 2 rows below. Is that also concerning? How do you determine which one is concerning?
I would, so we're on slide 147, and we looked at I on Math Course 7 as a modification index. I on Math Courses 9 is pretty big as well, but to me it doesn't make sense. I is defined at grade 7. Shouldn't be influenced by something happening in grade 9. It's, and once, by the way, once we have freed this, you should rerun the model with that free, and then maybe this is ignorable.
Exactly.
It can change drastically. But you have to exclude those that don't make absolutely good sense to you. It has to be very interpretable. Yeah.
I have a question on slide 157 in the model of the marital status and uphold.
Right.
You had said that you should say T1 through T4 at 0 to show that there are no residual errors. And I just wonder why that was in this when you have residual errors for the alcohol use and not.
So why we decided not to have residuals?
Right.
So why don't we have residual arrows here? Why are the residual variances fixed at 0? 2 answers. One, they're not needed. I don't know what the interpretation would be. Well, let me say 2 first of all. It's not identified. It's not a parameter you can identify. And 2, it's not needed if all you want is a change in the mean of the intercept factor, intercept growth factor. I guess if you have a residual variance here, you know, it's a residual variance that's the same for being married and not being married. Residual variance is not a function of the covariate value. So it would just be an extra description of the of the intercept variance here, and we already have an intercept variance parameter. So it's not a parameter that has any meaning, nor can it be identified, nor is it necessary for the interpretation we're after. Yeah.
I'm just wondering, why do we have circles for incremental change? Isn't it absurd?
Why do we have circles instead of observed here? Well, you can, first of all, we wanted to draw the analogy with the intercept growth factor. And second, we don't know what the value is. It's not observed. What's observed is the status. We don't know how big the effect is. You know, it's beta times status. We don't know how big that's going to be. So in that sense, it's latent. Yes?
Yeah. On the slide, are there real data where we have a real coefficient, not estimated or imagine the coefficient? That's a real data that shows the real coefficient. You understand what I mean?
No. So you're saying, what if we have...
Is there any data where we have a real coefficient, not the fixed one? I mean, not imaginary kind of example.
Data where we have real coefficients, not imaginary, that would only be data that you generate yourself in a Monte Carlo study. No, the idea is that the parameters are always population parameters that we don't know. We're trying to estimate them. There's also always that inference going on. Yeah, you never know what the reality is. It's...
No such analysis done so far.
Say that again?
There is no such analysis in the real world that has been done so far.
That where we actually know what the population values are?
Where we know that, where we can draw those coefficients, make some regressions, draw those different coefficients.
With true known values? No, I don't think so. Unless you observe the whole population, which you can do, I guess, in a small sample.
What simulation studies?
Yeah, no simulation studies. Yes, in the back. Hi, Mika.
I guess I was wondering about maybe an LPC question, but it seems like in traditional mixed modeling, time-varying covariates don't have any special status relative to time-invariant covariates. They're estimated basically in the same way as I understand it. Here it seems like you've given them sort of special status as latent variables and more discussion of interactions. Can you talk a little bit about the differences in treatment of time-varying covariates in this latent variable approach versus traditional mixed modeling approach?
Yeah, so the question is about the covariates. In that mixed linear model, we had the model where y is equal to, what is it, x times alpha plus z times b, where alpha is the fixed effect and b is the random effect. And there's not really a distinct difference made by the time-varying and time-invariant covariates. And here, certainly, in these models, we have emphasized it. The time-invariant covariates are predictors of the B's, so to speak, predictors of the, I would say, alphas and B's. The fixed part of this and the random part of this are going to be affected. I don't know what to say about that. I think that framework is expressed in a general way so that you don't talk about the specific model that might be applied. I think that kind of model can be used for the time-varying covariate modeling that we talked about. I don't know if this particular version can be used easily, at least, but at least the M1 and M2 models that we showed can be used, can be fit into that framework. But I don't think there is any. I haven't seen a distinction being made that corresponds to the distinction made in the latent variable framework. Yeah.
If I could ask a related follow-up. More pointedly, I guess I was wondering in that model where you have force 7 through force 10, with the direct effects from force 7 to force 10 over at 7 to that 10, would the typical analogy for mixed modeling be that you fix that slope estimate across the 4 direct effects from force 7 to force 10, and you get one parameter estimate for the slope of force on that force?
Mm-hmm. Yeah. Yeah, so in the mixed linear model, you would say that this coefficient has 0 variance. And it would be the same across time. Is that what you're saying?
Yeah, basically, although I was thinking about the M1 model where there's no STDC.
Yeah, yeah.
fixing the direct effects for 7
Mm-hmm.
across
Right. So if you start off with the mixed linear model, you have a random effect which varies across people, but typically equal across time. And you can certainly say that the variance is fixed, and therefore it becomes a fixed effect held equal. I do think there is some way in the mixed linear model to make it unequal across time by an interaction approach. But the standard model will probably be one that looks like this. Yes, person in front.
Similar question. I just on that model 2, when would you model those as interactions? We talked earlier you can actually create or define interaction terms. Would you be able to accomplish the same model with an interaction term, or the ST, DC, or whatever?
So you would create the product of home resources and course taking and include that instead.
Yeah.
Right. What you wouldn't get then is the idea that there is more variation in STVC than is captured by home resources alone. You know, these variables, this variable has a residual here. So you're capturing, this model captures that there are more individual differences in STVC than is explained by mother's education. So you would capture some of that by creating the interaction, but you wouldn't get the same type of model. You wouldn't account for as much heterogeneity as you do here.
But could you create an interaction between STCB and courses, and then predict math performance?
I'll create an interaction between this and this.
Yes.
Well, this one is latent, though. You would have to estimate its latent values for each person, yeah. Yes?
I was just wondering if you could clarify when you have to use individually varying times of observation.
So when do you have to use individually varying times of observation? It's only when you think it's important to account for, how should I put it generally, to account for important developmental differences that can occur by people at a certain occasion being of different ages. So,
Does it have to be by age?
no, it could be by something else also.
Something else at all?
Yeah.
Like progression of disease?
Yeah, yeah, exactly. If progression of the disease is the time axis, at a certain occasion, so that's a time variable, right, you're saying? So the outcome is something different. Yeah, as long as there are important individual differences with respect to the time-related variable for individuals at a given time, given measurement occasion. The classic example is you come in for treatment for some problem, and then you're supposed to be seen again in a month. And some people come after 4 weeks, some people come after 6 weeks. So the second measurement occasion, people will differ in post-treatment time lapse between 4 and 6. If that's developmentally important with respect to the outcome that you measure, then you should take that difference into account. Very often it's trivial, so you can just give it time score 1 for all of those people. 4 weeks, 6 weeks, it's the same thing approximately. So just say time score 1, time score 0 being for the first time point. But sometimes it's very critical, and then you want to take it into account. Yes?
We have a question?
Yeah.
For the status change model, could that be parameterized with lag effect of the status change variable and some equality constraints on those lag effects? Or do we gain something by using the latent variable to represent status change?
So the question is about slide 157 and possible lagged effects of status change. Well, in a sense, though, the way Linda talked about this, it's already lagged that this change is not only a change for time 1, but also...
Oh, I took away the wrong one.
That's right.
Put it, sorry.
Somebody pulled the plug.
No, now I put it back. Oh, well, I'll go back.
I'll go back.
No, I just thought it would be easier for you to talk about it with, we're going to be going back and forth here.
So, but maybe your question is, if this is fixed at 1, could that be estimated free, different from 1? The way it is now, it's 1, 1, 1, 1. So you drop down the same amount for all of those subsequent time points. So there is a lagged effect, but it's the same as the current effect. So the question is, could you estimate that different from 1? Then it would have to do more with the slope changing than the intercept.
Actually, what I'm thinking of is, could you do without those incremental change-like variables and just regress
regress.
Y1 through Y4 on status change, but hold all those parameters equal?
Oh, I see what you're saying. So we regress the y's directly on this with equality constraints.
Yes.
That's the same thing, yes. Look at the indirect effect. It's 1 times minus 0.29, 1 times minus 0.29, 1 times minus 0.29. So yes, it's the same thing as holding these equal. I mean, holding the regression of y1 on this equal to y2 on this, y3 on this. Yes, exactly the same thing. Yes?
On the piecewise linear, piecewise change.
Do you have the slide maybe?
Yeah.
Piecewise, folks.
Can you, 120?
Okay, we got it.
120.
Right.
Can you also estimate the change point? Can you free that instead of 1, 2, 2, 2, 2? Could you do 1, 2, 3, 2, 3, 3, 3? Fix the constant.
Have something be free.
The same, but the same, and then I don't know. You'd have to free something on the second. I mean, is there some way to estimate the change point if you don't know it?
So the question is, slide 120, can we estimate the change point? So that's an interesting story there. This type of approach assumes that there's a meaningful time point where the slope changes. And it implies that that time point is known, makes substantive sense, is known, and is the same for every individual. Now, in other applications, the time point may not be known, and it may vary across individuals. And that's a topic of growth modeling called change point analysis. Change point analysis. And that's typically not done in the maximum likelihood framework, but it's done more in the Bayesian analysis framework. So there are examples of this where you talk about a disease progressing, and here kicking into a more dramatic worsening, and you want to estimate that point, and it varies across individuals. Or an intervention that has an effect at a certain time point and may be different for different units in your sample. So there is a literature on that, which is quite interesting. It's more advanced modeling than we're talking about here. It's topic 4.5.
We have one question over here. Right.
On slide 125, where you have parameter estimates for different slopes, slope 1 and slope 2, can you use the statistics up here to test the difference between, say, slope 2 for mother education minus slope 1 mother education?
So the question is on slide 125, and does home resources have different effects on S1 than S2? That is 0.047 significantly different from 0.269. Yeah, so that can be done in two ways. The easiest is to do it by model test, which is a so-called walled test. And in this case, it's a special case, which is the, I guess it's called a correlated t-test. So you take the difference between the estimates, and then you want in the numerator and in the denominator you want the standard error for that difference, and that standard error draws on the standard error for each, but also the covariance between the parameter estimates, which you get out of Tech 3 in Mplus if you want to do it by hand, but you get the same thing if you use model test.
Or a difference test.
Or a difference test, yeah, which is then
Either a chi-square or log likelihood difference test where you let the parameters be free in one model and hold them equal in the second model, and then you can do the difference test. It's probably easier to let us do it by using model test.
So it's a difference, two tests that are asymptotically the same. One is drawing on weighted least squares theory, the other is drawing on maximum likelihood theory. Yes?
Could you set it up a different way by making the parameters on your line, the way you set the timing up for S1 is 0, 1, 2, 3, 4, 5, and then adding 0, 0, 0, 0, 1, 2, and then you've separated out the effect on the first part of the slope, and then you've added a second slope on?
Wait, could you say that again? So related to, could you say it related to slide 1, 2, 3?
Are you talking about the time scores?
So S1 has math 7, 0, 1, 2, 3, 4, 5. And then IS2 has 0, 0, 0, 0, 1, 2. So now you've got that S1 is operating on the whole time frame.
Mm-hmm.
S2 picks up at the change point.
Right. Yes. So let's see. You're saying S1 influences the whole period, and then S2 is just adding to that for a certain period. Yeah. If you find that easier to interpret, yes. Here, you keep the two parts more separate, but if that fits in with your substantive thinking better, it would give you the same result, I think. Yeah.
And the S2 regression on the home resources say it would just be for the inputs on the second part.
Okay.
Yeah, well, I guess that's where it falls apart, that you haven't separated the two parts for when it comes to regressing on covariates.
I just thought I might answer that question.
Do you want to say something?
Oh, just that I put all the receipts on the desk pack on this side, and then another one on the other side, so if you want to pull those out. The other thing I wanted to say is, please bring your badges and notebooks back, because there aren't any, the folks who are signed up for tomorrow, there'll be none left, so please bring yours tomorrow.
Okay. So we should
Do you want to
probably...
repeat that?
Could you repeat it, because I didn't hear what you put back there.
Okay. The receipts.
Oh, the receipts. Okay.
I put a pile on this table back here, and then another pile on that table there. So as you're going out, you want to grab a receipt, and you just fill it in.
And bring your badges and your handouts back tomorrow.
Yeah, you just don't have any more badges, and very few handouts, and those are for people who are signed up for tomorrow.
And let's come back here at 3:25. We have to leave here by 5 o'clock. Well, 3:25.
Oh, I thought you said 45.
Oh, no, 25.
Okay.
25. And because we have to leave by 5, the room.
All right, folks. See you.
We still have a lot to go over.
Folks.
Let's take our seats so we can get started, because it's almost 3:30, and we have to actually start exiting the room at like 5, no later than 5 to 5, because they want the room empty at 5 o'clock. So that gives us not too terribly much time. So let me just, while Bengt is taking a little rest there, talk a little bit about some computational issues for growth models, some of which we've touched on, but just to summarize them. So one of the things that we've already talked about is if the observed variables decrease over time, this could make the modeling more difficult. So that's one thing to keep in mind. And there's also an issue of the scale of the observed variables. So in your model, you may have observed outcome variables, and you may have observed covariates. And it's a good idea not to have one that has a variance of 4,000 and another that has a variance of 0.4. You want to try to keep the variables with similar variances. And you can rescale a variable by dividing it by a constant, and this will not change its relationship with other variables. That's continuous variables we're talking about, not categorical. So this often gets people into trouble. You know, I'll see something come into support, and you know, I'll notice that they just have huge variances, and if they just use define to rescale by dividing by a constant such that the variances are between 1 and 10, this can aid you very much. And but when we say rescale by dividing by a constant, that's what we mean, divide by 10 or divide by 100. We don't mean standardize the variables. So that can help. And we can have convergence problems which can be related to starting values or to the model. And sometimes the program just stops because the default number of iterations has been reached. And if that happens, then you should check the partial output and see if you have any negative residual variances. That's often a problem. And if you don't, then you can either increase the number of iterations or give some starting values to the model. And actually, I'll say one thing about version 6, and that's that whenever a model doesn't converge, starting with version 6, we will give you model command statements including starting values. Then the starting values will be the ending values from the non-converged run. So that should help you. So anyway, and then another thing, you can use those, because I was actually documenting this a couple weeks ago, and I thought, oh, you can use those commands too in model population when you do a Monte Carlo study, even when an analysis, you know, converges and you want to use the converged values for population parameter values in model Monte Carlo. So that's going to be very useful, I think. But anyway, if you have large negative residual variances, you can try these starting values that we're going to give you. But it may just be that there's a problem with the model, and you may have to just start troubleshooting the model a little bit. But if it stops before the maximum number of iterations has been reached, check the scale of the variables. That's something that gets people a lot. And it is the case that if you have a combination of categorical and continuous variables, that's when it's mostly a problem. So people will go, you can go along really well with continuous dependent variables that have big variances, but if you then bring in a categorical dependent variable, it's not going to work. And another thing you can do is try new starting values. Now, although we'll be giving you these statements that have starting values for all parameters, really the most important parameters to give starting values for are the growth factor mean and residual variances. So giving them like for factor loadings and stuff is usually not necessary. There are special convergence problems for models using the bar symbol with at after it, and also with on and x with after it. And this comes about because oftentimes the effects are not random. And so what you can do is look at the partial output and look at the variance of the parameters that are being estimated using the bar symbol, and it's likely that you'll find that their variances have gone to 0, in which case it's telling you it's not a random effect, it's a fixed effect, so you can just estimate it as a fixed effect. So those are some computational issues for growth models that I forgot to go over before the break. And now Bengt is going to talk to you about regression among random effects. And we only have one hour.
All right, folks, we have some excitement to deliver here. Since we have a representative from Gothenburg, Sweden here today, welcome, Magnus. We then want to show an old JASA article, Journal of the American Statistical Association. I think it was Nils Blomqvist, somewhere in the departments there at the university. 1977, talking about blood pressure. And blood pressure seems to have stirred up a lot of excitement over the years. Take your time. But here it comes about in the context of regressions among random effects. The standard multi-level model looks like this. Level 1, how easy it seems now, right? 3:30 in the afternoon, whereas 8:30 in the morning, it was tough looking. Level 2, we know what that is. And we know how to draw equations 1, 2, and 3. We draw it like on the bottom left. You know, we just do that schematic, and we know the whole story. That little picture tells us everything. Everything about what it means and everything about how it should be set up in Mplus. So it's a quick schematic. But that modeling is a little limited, isn't it? For instance, on level 2, you never see a random effect on the right-hand side of the equality. They're always on the left-hand side. But the ideas of Blomqvist and others is that we could put say, eta 0 on the right-hand side of the prediction of eta 1. So the initial status, for instance, can influence the growth rate. So there you have it, a new type of model. So equation 4, you should draw a little connection here to the picture on the right. So it says that, yes, W has an influence on the initial status, and therefore, W has an indirect influence on eta 1 via eta 0, so this way. W may also have a direct effect on eta 1, but it may not. It may be sufficient that W influences eta 0, which in turn influences eta 1. So I'm saying that even though on the left-hand side, this arrow, influence of W on eta 1, the slope, even if that's significant, this direct effect may not be significant, right? This just says that as W increases, eta 1 increases, but that same phenomenon can happen if W increases because eta 0 increases, and eta 0 increasing influences eta 1 to increase. So you may not have a direct effect there. In any case, these two models correspond to two different ways of thinking about the situation. Here, the two growth factors are on the same of the same status. They're both dependent variables. So it's bivariate dependent variables influenced by the same covariate. And we're not saying anything about how one influences the other. We're just saying that the residuals can be correlated. Here, however, we're saying that eta 0 has a special status in that it influences the growth rate. You can imagine in achievement modeling could be that initial status, how much you knew about growth modeling when you came into this course this morning, influences how quickly you learn. You may be, if you had some preparation, you may be able to pick up on more of the details, and your growth rate skills over the hours here may be on a higher slope than otherwise. So you're really formulating a hypothesis that starting point is of specific interest. Now, these two models are statistically equivalent. If you count the number of parameters here for this part of the model, we have 1, 2 slopes, 3, 4 variances, 5 covariance. And on the right, you have 1, 2 slope, 3, 4, 5. Same number of parameters. And note that you cannot identify also the residual covariance here because you already have the regression parameter here covering their relationship. So these two models cannot be statistically disentangled. In certain cases, they can be, but not in this simple case. So it's largely a matter of substantive choice how to interpret this. And Blomqvist was interested in how blood pressure level at a certain age influences the increase over age. Because we know that blood pressure goes up with age, and for other reasons as well. But he wanted them to see if the level, if people at higher blood pressure perhaps had a at a certain age had a higher increase with age. I have no idea what he found. You have to go to Gothenburg for that. Here's another model of that ilk. It's a little bit more advanced, and this relates to work by a colleague of mine who is interested in this. In the educational setting, it's often the case that you're interested in the regression of S on I. Actually, a colleague of mine, Michael Seltzer, did this where he was interested in this slope, how much the growth rate depended on the starting point, varying across schools. So a multi-level topic that we talk about in topic 8, a year and a day from today, if it all goes well. But here we are in the single level context, or no clusters, no schools. So here the idea is that instead we have an interaction now. On top of the S on I feature, we're now adding yet another complication, an interaction, where it's an interaction between a covariate and a latent variable. And we note that that's shown as a filled circle. So we're saying that the interaction between the starting point and your course taking influences your growth rate. So you have the main effects here and here, and you have an interaction effect there. Excuse me. So let's go forward here and backwards here. No, forward here. So how do you do that modeling? Well, if you look at the bolded entries on slide 163, you have centering, grand mean centering. It's just subtracting the mean from math course 7 so that the mean of that new centered variable is 0. That tends to make interaction modeling more easily interpretable. And now we have the growth model on slide 163. And in this case, it's going to be preferable to use parameterization 2. We talked about parameterization 1 and 2, 1 being the one where the intercepts of the outcomes were fixed at 0. That's the one we get by default by Linda's bar language. And we're going to now change that by instead holding those intercepts equal. That's that new parameter that we showed on that slide. And when we estimate that single intercept parameter, we have to fix the growth factor mean, the intercept growth factor mean at 0. And it's going to be, just like we centered the observed variable, we are now, in a sense, centering the I variable to have mean 0. Again, that makes the interpretation of interactions easier. And then we're going to introduce a new bar statement which uses the xwidth command. I'm going to show that here also. So we're going to use the xwidth command here on the left screen, which says that we are interacting I with math courses 7. We're creating the product of the two, and we're calling that inter as an interaction. So we're creating an interaction variable, which we want to use this approach when one of the two variables is latent. Both of them can be latent, which then covers variable interaction models of the kind. Am I fading, or is it just me? Do I need new batteries? You hear me? Okay. Andreas Klein has written a psychometric article on latent variable interaction modeling, and in Mplus that's handled by xwidth. Here, only one of the two variables is latent, but it's the same idea. Once we have that interaction variable, then, we can use that in regressions on the right-hand side. So S would be regressed on the interaction, as here, there's the interaction, and S can be regressed on that interaction. S on I, that's B1. S on Math Courses 7, that's B2. S on interaction is B3. And then in addition, we have I on Math Courses 7. So basically, this is asking the substantive question, do students who have a high initial status of math performance in grade 7 benefit more or less from course taking? Or rather, from a given amount of course taking, who benefits the most? Those who have high or low initial status. Maybe that's a more reasonable question. For a given amount of course taking, do those who have a high versus low initial status benefit more? So let's see what happens here. Well, we have this. We have random slope features here, so we don't get any chi-square. We get a log likelihood value, and we get our Dirac value. You check that the model is set up right. And you have S on I and interaction. And the interaction is significant negative, minus 0.047 significant. S on math courses is significant. I on math courses is significant. However, now our task will be, we're forced to interpret what this minus 0.047 means. So how on earth are we going to understand what minus 0.047 means? Well, we have to go to the next slide. Well, actually, 2 slides forward, 168. So we have the model equation for the slope. The slope is equal to A plus B1, the first slope, times the I variable, B2 times math courses, B3 times the interaction, I times math courses, plus a residual E. Or, using a moderator function, a term that was used in Klein and Mosberger's 2000 psychometric article, we can look at I as moderating the influence on Math Courses 7 on S. So let's stay with that for a second. S is regressed on I and Math Courses 7, but the influence of Math Courses 7 on S is not a single coefficient, a single slope, but it's a slope B2 plus B3 times I. So I moderates the influence of Math Course 7 on S. This is called a moderator function consisting of a fixed coefficient and a coefficient B3 times I that varies as a function of the individual's I values. This is one way of expressing an interaction as a moderation. And this seems like a substantively reasonable way of formulating it, that a given amount of math course taking has a different influence on the growth rate S for people with different initial status. So you estimate the model, you get the unstandardized coefficients, but again, in this case, math course taking and I are on different metrics, so it perhaps is useful to standardize those variables, or rather standardize the coefficients. So we're going to standardize the coefficients here with respect to I and math course taking 7. And standardize with respect to right-hand side variables, independent exogenous x variables, means that we multiply by their standard deviations. So we this coefficient, 0.087, gets multiplied by the standard deviation of I to get this standardized value. And likewise, the math course taking 7 coefficients gets multiplied by the standard deviation of math course taking to get this standardized value. So in this case, I just did that by hand, actually. And then, when you're down there at the bottom of slide 168, you are now ready, in principle, to interpret this substantively. And you can say, for instance, at the mean of I, which is 0, the slope increase is 0.04 for 1 standard deviation increase in math course taking. How can I say that? Well, if the mean of I is, if you're looking at the mean of I, the value is 0 down there. So the moderator function is simply the first term, 0.04. So that's where we get the 0.04. At 1 standard deviation below the mean of I, which is 0, 1 standard deviation below the mean of I, it's I is equal to -1, right? So -1 there will be minus 0.04 times -1. That's plus 0.04. So the coefficient will be 0.08. And 1 standard deviation above the mean, the slope does not increase as a function of math course 7 because it would be 0.04 minus 0.04. So if you just read these, now you come from there to here, so just look at this and think, what does this mean? So who benefits the most? A person who has the mean. Who benefits the most from math course taking? A person who is at the mean of initial status in grade 7, 1 standard deviation below the mean, or 1 standard deviation above the mean. Yeah, here, 0.08 gives the best, right? So the people who benefit the most from being here are those who knew nothing about growth modeling. All right, you're with me. Next.
Okay. Oh, thank you. Okay, so now we're down to growth modeling with multiple processes, which was on our list of various special things you can do in the latent variable modeling framework more easily than in other frameworks. And so what we're going to be looking at is parallel processes. Now, multiple processes can also be sequential processes, parallel processes being processes that are happening at the same time, and sequential processes that are happening one after the other. Thank you, messed me up. Okay, so let's talk a little bit about how we would do this. So in our situation, we're going to be looking at the math achievement and math attitudes. So that's going to be our parallel process example. So Bank showed you earlier that the LSA data had the math scores, and they also collected math attitude information. So the first thing that you would do would be to estimate a growth model for each process separately. It's unclear, that they're going to have the same shape. We don't know that, so we have to investigate each one separately. You want to find a well-fitting growth model for the two processes. And the reason we would want to then put them together is because we want to understand how they relate to each other. We want to look at the relationship between their growth factors and other things. Now, the first thing you would do is, as we said earlier, is determine the shape of the growth curve from theory, the data, whatever, and find a well-fitting model without covariates, and then modify the model if necessary. And once you're satisfied, then you would put both of the processes together, and only when you have that working would you bring covariates into the model. So as in all data analysis, it's really a good idea to do it stepwise in an organized fashion so that you can catch what's going on. If you try to just estimate both growth models at the same time with covariates, if it doesn't work, you have no idea why it's not working, then you have to go back and start at the beginning. So it's best to just go through the process slowly and carefully. So now we already know about the LSAT data. We talked about it earlier. And so now we're going to be including not only math achievement, but math attitudes from grades 7, 8, 9, and 10. Okay. All right. So you're familiar with the picture at the top. We've been looking at that a lot today. The mean growth curve for grades 7, 8, 9, and 10 on math. But then let's take a look now at the sample means for the attitude toward math. We see that from grades 7, 8, 9, and 10, the math attitude goes down. So the person's attitude toward math decreases, and it looks also fairly linear, although we did find a free time score model, at least for the later grades, worked well for grades 7 through 12. So what we were interested in doing then is getting a good growth model for both of them, and then once we have that, estimating the parallel process growth model. Okay, so on the screen here, we see what that model looks like as a path diagram. So on the top, we have our growth model for math achievement. And we've seen this a lot today, so we know what this means. IM is the intercept growth factor for math. SM is the slope growth factor for math. And in the bottom of the picture, we have the growth model for math attitudes. And it's looking similar. We have an IA is the intercept growth factor for math attitude, and SA is the slope growth factor for math attitude. And you can see that we have one covariate, mother's education, and all four, IM, SM, IA, and SA, of the growth factors are regressed on the covariate mother's education. And we see that we have some residual covariances among the growth factors. We have a residual covariance between the intercept growth factor for math and the intercept growth factor for attitude. We have between the intercept growth factor for math and the slope growth factor for math. And down here we have the intercept growth factor for attitude and the slope growth factor for attitude. And here we have also included the slope growth factor for math, the residual covariance for the slope growth factor for attitude. So these are designated by the arrows. Now, additional parameters we could have in the model would be, we could have residual covariances between the residuals for math at grade 7 and attitude at grade 7, and the same at grade 8. But these are just suggestions to you of other parameters. Oh, and that's something I thought about actually when I was listening to Bengt, and that's that what we're trying to do, our goal in showing you all these different models, is to give you suggestions for what you can consider for your own research. Many of the models may not be appropriate, and so they're of interest and tucked in your brain for some time later in case they are necessary. You get into some new type of data that they would be good for. But we're trying to give you building blocks, things that you can put together and come up with your own unique model. So we never give you everything. We can't possibly show all possible models that can be run in Mplus, but we try to give you a flavor of the flexibility and ideas for your own research. So the growth factors are in, well, let me just come to the other screen and go on for that. So we're interested in understanding the correlations between the growth processes. We have two processes, and we wonder, we might wonder, well, gosh, I wonder what the relationship between where people start in math and their attitudes when they start in grade 7. Wonder if there's some relationship between where they start in math achievement and what their attitudes are at that grade. Or as we know, we are interested in the relationship between intercept and slope growth factors for each individual process, but we're also interested across processes. So we can look at the correlation between the processes through how they go through the covariates, through their relationships there, or through the residuals, as I showed you, and also through the outcome residuals, as I also showed you. So there are a lot of ways that they relate to each other. It can be quite complicated. And it's our job to, when we estimate one of these models, to see how that works. Okay, so let's look at the input. So you can see now the used variable list. We've now added the attitude variables, ATT at7 to at10. And now we're only using one covariate, mother's education. So we've taken the other two covariates off of the used variable list because they won't be used in the analysis. Okay, so let's look at our model. So in this situation, for math, we're using a model with free time scores. So we have math 7 at 0, math 8 at 1, and then we're going to estimate the time scores for math 9 and math 10. And just by mentioning them, they're free parameters. Earlier, we put an asterisk with a number, and the asterisk allowed us to give a starting value. But here, we're not going to give a starting value. We're just saying that they're free parameters. For attitude, we're going to have a linear model. So our time scores are 0, 1, 2, and 3. And then we can say IM-SA, which is the list of IM, SM, IA, and SA, and we're regressing that on mother's education. Now we're still in a situation where we get some chi-square tests of fit, and RMSEA looks pretty good. And we have a smaller sample, so we can see the p-value is at least not all zeros for the chi-square test of fit. But what we're mostly interested in here is looking at these regressions. So the two growth processes can have different relationships to a set of covariates. And actually, one could use different covariates for the two processes. As far as mother's education goes and the relationship to math, we see what we were seeing, that it's significant as far as where the students start in their development in math in grade 7, and it's also significant as far as how they grow. Now with math attitude, neither mother's education is not a significant predictor either of where the students start or how they grow. However, what we can look at then, let me actually put this over on the other screen. But what we can also, besides looking at the covariates, we can look at these residual covariances among the growth factors. So for example, let's think about grade 7. Let's look at IA and IM. So that's here, IA with IM. So that's looking at the relationship between the intercept growth factors for the two processes. And we see that it is positive. So people with a higher attitude are going to have the higher math scores, and lower attitude, lower math scores. And that makes perfect sense. And then down here we have the slope growth factor for attitude and the intercept growth factor for attitude. And we see that they're negative. So people who start low tend to get an increase in their attitude, improve their attitude more than those who start high. Those who start high, their attitude grows more slowly, or it goes down more slowly. So we're looking at a negative relationship here. And another one we might want to look at is IA with IM. Oh, we looked at that one already. I'm sorry. So that here we can get an idea about the relationships. Like, let's see SA and SM. Where is that? Here it is. Okay, so that's both of the slope growth factors. So the average growth rates in attitude and math, how do they relate? Well, they don't, that's barely significant. It doesn't look like there's really much of a relationship if you account for the fact that you should be conservative in how you look at this. So this is how one would look at a parallel process growth model and what one would be interested in getting out of it. You get out the relationship between the two processes, and you see also how the variation in the process is explained by covariance. And I think it's oh. Plenty.
Good.
Yeah.
Good. Well, does your head hurt yet? If not, maybe now it will. The end of today, we're going to prepare ourselves for tomorrow. And we're going to do so by expanding our capabilities of modeling different kinds of data. And it will come in very handy in several contexts, including the exciting modeling of data with strong floor effects, strong floor or ceiling effects, what Linda called the modeling of zeros, the two-part modeling, where this is a building block that we need to use. So again, on the left screen, we have formulas. On the right screen, we have pictures. And I'm looking at you to classify you into two classes. All right. So you have then a quick repeat of what we talked about last August in topic 2 with focus on logistic and probit regression. And we're going to put that into a growth modeling context. So let's see. We start with equation. We give everybody a chance, however, to, if they have sinned and not prepared for this, they still have a chance by looking at equation 22, which says the same thing as the picture on the right here, these S-shaped curves. So we're going to, instead of having a model that predicts values of a continuous outcome like y, we're going to talk about a model that predicts probabilities, and probabilities for a categorical binary variable, dichotomous variable. In this case, we call that u in Mplus notation. Categorical variable is called u instead of y, and u assumes the values of 0 or 1. And we talk about the probability of being in the highest category 1 as a function of, in this case, two x variables. And that function is f, parenthesis, beta 0, which is an intercept, and beta 1x1, beta 2x2, the two slopes multiplying their respective covariate. So that looks very much like linear regression inside of the brackets, except we have a function f. And f is a function that turns that linear expression inside the bracket, the linear argument as it's called, into something nonlinear. And we want it to be nonlinear because we want to force the probability to lie between 0 and 1. Otherwise, it wouldn't be a probability. And one function that does that is a distribution function in statistics. And there are lots of different distribution functions. Two common ones are the normal and the logistic distribution function. And the normal distribution function is called cap phi or phi. And the logistic function, yeah, wow. That's the kind of music we need at this time of the day. The logistic function looks like this. 1 divided by 1 plus e to the power of minus z, where z is called the logit. Wow, we have all kinds of entertainment. This one, the logistic, you can actually, for a given z value, you can do your computation on the, we used to say on a hand calculator, and now you say you do it on your phone. The normal, it's not explicit, you have to look it up in tables. Maybe they have that on the phone too, but I doubt that that's a common app.
Exactly.
Maybe among us nerds it would be. All right, anyway. So let's take an example, and we try to be pedagogical here and have two different kinds of x variables, one binary and one continuous. Years spent in a coal mine. And the question then is, what's the dependent variable? It's developing lung cancer or not. And we look on the screen here, and the estimated model may look like this. The ultimate result can be brought back into a picture relating the probability of lung cancer to the two x variables, x1 and x2. And since one x variable is binary, smokers, non-smokers, we can show the results as two curves, each one of them related to x2, years spent in a coal mine, and the only difference being a shift sideways of the curve due to x1 being 1 or 0. And we know then from regular regression that when x1 is 0, that the intercept is beta 0, but when x1 is 1, the intercept is beta 0 plus beta 1. In both groups, however, the slope of x2 is beta 2. That is, they have the same slope, these two curves, but they're just shifted sideways. So for instance, for a given number of years in the coal mine, the probability is much lower to develop lung disease for non-smokers than for smokers. So that's all we have to say really at this point. You can interpret the model in terms of just the signs and significance of beta 1 and beta 2. You want to know if beta 1 and beta 2 are significantly different from 0. You want to know if they're positive or negative. So beta 2 is clearly positive here. And that is, the probability goes up as a function of x2 going up. And beta 1, is that positive or not? Yeah, it gives a higher probability, right? So beta 1 and beta 2 must be positive here. And you can stop there. That's all you need to do. You can talk about significance and sign, and perhaps even plot the results like that. You don't need to know anything more. But you can also increase the level of ambition and get into odds and odds ratios and estimated probabilities we're already using in that plot. So now you know everything about logistic regression. And I'll just scare you off here with slide 187, which can be penetrated by grade 8 algebra. So you define an odds as an odds that you're going to develop lung cancer. It's probability of as a function of x, probability of developing probability of developing lung cancer divided by probability of not developing lung cancer. Not developing it being 1 minus the probability of developing it. So it's just a ratio of probabilities. If you assume the logistic model as opposed to the probit model, the one that can be calculated via your cell phone, it's going to be simple in the sense that you're going to get a log odds that's linear in x. And whenever you get something linear, it gets easier to interpret. So if we're then going to talk about the logit, a logit is the same as the log odds, which is the log of the probability ratio, because that's what an odds was. And if we insert here in probability u equals 1, the model that we are assuming, put that inside of the bracket, take the log, and, you know, abracadabra comes out here, a linear function of x. So these steps you can do tonight before you go to bed. So as it says that as x increases, the logit increases beta 1. As x increases 1 unit, the logit, the log of the odds increases beta 1. Sometimes you like odds better than log odds. Well, to get from a log odds and odds, you take e to the power of, or exp, on your cell phone function, exp, and that is the same thing as taking e to the power of beta 1. So e to the power of beta 1 tells you how odds change as a function of x, whereas beta 1 tells you how the log odds changes. And that's what we say here on slide 188. And now you're close to knowing more than you want of logistic regression. So we'll just point you to the books that you should have all read until today. No, but so there are some really good books here, Agresti and Agresti Lite. And a sleeper here, a really good book, good text, very thorough in terms of the formulas. However, what we're interested in is growth modeling with categorical outcomes at 4:15 on a Monday afternoon. So there, look at that. Pick your screen. We still have the idea that we started off with this morning of individual differences in development over time. But now we're talking about individual differences in development of probabilities, not values of a continuous outcome. But it's individual difference in development. That matches the interest of psychology and statistics. That is how you want to formulate growth models. Let's consider the logistic model version of this, although Probit would be going along very similarly. So the logistic model considers growth in terms of log odds, logits. So you have as a dependent variable the log of the odds of u equals 1 divided by u equals 0 as a function of growth factors eta 0, 1, 2. In this case, it looks like quadratic growth, and x, your time scores. So we have formulated this in terms of log odds. So if that's the first encounter you have, it can be scary. But if you go back and realize that all that is saying, looking at the log odds that's linear like that, all that's saying is that you have an S-shaped probability curve for the probability u equals 1 as a function on whatever you have on the right-hand side. So it's nothing really mysterious. It's that sometimes in the description in books or papers, the author scares away half of his or her readers by going straight to this, which for them, by the time they have finished the book, they just want to write in shorthand and not take too long time. So anyway, this is for a binary outcome using a quadratic model with centering at time c. Centering here because we subtract c from the time scores x in both the linear and the quadratic term. And note here that x has t and I as subscripts, so we are allowing for individual differences of of observations in the timing and the ages. Now we still have the same level 2 equations. We have an equation for the intercept, the linear slope, and the quadratic slope as a function of a time invariant covariate W. So it's only the first level, the level 1 equation that has changed. The level 1 equation corresponds to a logistic regression of u onto the growth factors, essentially. The level 2 equations, however, corresponds to linear regressions. Well, these are standard linear regression because the dependent variable is a continuous variable. It is latent, but it is continuous. And the important part is that it's continuous, and therefore it's a linear regression, whereas level 1 is a logistic regression. So now, I don't know, we talked about 2 parameterizations here, and we get to parameterization 2 in this case, where we're going to talk about, instead of intercepts, as we've talked about so far, we're going to talk about thresholds. That's the counterpart for intercepts when the outcome is categorical. So now we switch over to parameterization 2, because we have categorical outcomes, and we have then equality of thresholds over time, and then we have to fix the intercept factor means to 0 to not have unnecessarily many parameters. And for now, we're going to ignore this last third bullet because we're going to stay in the maximum likelihood framework. And with that, it's time for Linda and the final riveting example.
I don't know how riveting it's going to be. But anyway, I'll do my best. So we're going to take a look at an example, data from the NIMH Schizophrenia Collaborative Study. And in this study, they look at schizophrenia data. There were 64 people using a placebo, 249 on a drug for schizophrenia, measured at baseline in weeks 1 through 6. So we're going to be looking at a severity of illness variable that's binary, and we're going to be looking at it at weeks 1, 2, 4, 6, and including a treatment variable. So this is a diagram of what this looks like. So the outcome variable is measured in proportions here. Here are the weeks, 1, 2, 3, 4, 5, 6. The placebo group is up here. The drug group is down here. There was random assignment to placebo and drug, so this should not be different where they start, really. And you can see that this is looking at it after the study. You can see that the placebo group declined, but the drug group declined more. And I guess the question here is this difference at the end significantly different? But now we're going to look, as the first part of this example, we're going to look at and here's the model. So illness, the binary variable at time 1, 2, weeks 1, 2, 4, and 6. Note that there is no residual here because it's a binary, these are binary variables. We have the same model we've seen all along, I and S, and we rest them on drug. So nothing new other than the fact that the dependent variable is now categorical, and instead of talking about values, we're talking about probabilities. So here we have a new option, categorical. So if a dependent variable is categorical, it needs to be put on the categorical list. Any variables that are not on either the categorical, censored, count, or nominal lists are assumed to be continuous. So here we're identifying illness 1 through illness 6 as categorical. The program actually determines the number of categories, so no other information has to be given, and the variables are recoded. That's described in the user's guide, but basically the categorical variable should have the lowest category assigned as 0, and then subsequent categories 1, 2, 3, etc. Now you can see I'm using the use observations option because we're only going to look at the treatment group now. So we're saying use observations is drug equal to 1. And also I have bolded Tech 10. So here, our primary interest right now is going to be talking about Tech 10. And Tech 10 provides univariate and bivariate information about model fit. So when you have categorical variables and you're using maximum likelihood, you're not going to get traditional fit statistics. And Tech 10 is a really good way, even if you do get traditional fit statistics, to understand what's going on in your data. We look at the univariate and bivariate patterns along with response patterns to try to determine where the data aren't fitting, where the model is not fitting the data, rather. So well, I just want to go back to show you one thing. Actually, I think I'll do it over here because people can see the bottom, certainly can't see the bottom of that screen on that side of the room. Okay, so here we have our model command, and we specify it exactly the same way as we do 0, 1, 3, 5. So what is 0? Why do we have 0, 1, 3, and 5? We've been having 0, 1, 2, and 3 all day. Well, these are non-equidistant time points. We measure at time 1, time 2, time 4, and time 6. And remember, I said that you had the time scores have to reflect the distance between the measurements. So 1, 2 is 0, 1. And then we go to 4, which is 3 minus 1 is 2, 4 minus 2 is 2. So that's time score 3. And then for 6, it's time score 5. So the time scores reflect the fact that we have non-equidistant measurement occasions. And because the categorical option is used, then Mplus will do the growth model parameterization where the thresholds of the categorical variables are held equal across time, and the intercept growth factor mean is fixed at 0, and the slope growth factor mean is estimated. Okay, so that's our input. And we have our test of model fit as usual. And you notice that we don't get chi-square or anything because we're using categorical outcomes and maximum likelihood estimation. If we estimated this model using weighted least squares instead of maximum likelihood, we would get traditional fit statistics, and but we would be doing a probit regression rather than logistic regression. Now, here is something that we do get. Here is two chi-square tests that we do get: the Pearson chi-square and the likelihood ratio chi-square. And what are they? They aren't comparing the H0 and the H1 model like the chi-square we're used to. These are chi-square tests of model fit for the binary and ordered categorical variables in the model. So they're frequency test chi-squares. So if you have 5 binary items, it's the 2 by 2 by 2 by 2 by 2 table. And you want to compare the observed and the estimated frequencies to assess model fit. These particular tests are known to be not very meaningful if you have more than 8 variables. So, and if they don't agree, then you shouldn't interpret them. So there's two things. If you have more than 8 variables, they probably aren't very reliable. And if you have less than 8 and they don't agree, one says the model fits poorly and the other says it fits well, then you should ignore them. But here, there's universal agreement that the model does not fit well. So then the question is, well, why doesn't it fit well? And we're going to take some time now to look at Tech 10 and see how we can use Tech 10 when we have categorical outcomes to figure out why the model doesn't fit well. Whoops, I went too far. Oh. All right, well, let me start with the beginning of the output and then go on. So in Tech 10, it's model fit information for latent. We say latent class indicator part of the model because I think we developed it for mixture modeling, but it can be used for non-mixture modeling. And first, the response patterns. So what are those? So we have 4 variables, and they're binary. They can take on a value of 0 or 1. So pattern 1 are people who have 1 at the first time point, 0 at the second and third, and 1 at the fourth. Pattern 2 is somebody who had 1 at the first time point and 0 at 2, 3, and 4. So you can see that. So this is just a lookup that we have so that we can know when we get information for number 1 which pattern it refers to. So for example, here okay, and then this is the next part of the output, which I should probably put over here since it goes down so far. Okay, so what do we have? So we have the response pattern. Could you poke that back? Thank you. Okay, so we have the response pattern, and that is referred to over here. So for example, 1 is the first one there, and 2 is 1, 0, 0, 1, or I can't see that far. Yeah. 1, 0, 0, 0. Okay, so this is how this relates. Response patterns, response patterns. Then we have frequencies, observed and model estimated frequencies. Then we have standardized residual, which is the z-score. Then we have the chi-square contribution, the Pearson chi-square contribution, and the log likelihood chi-square contribution for each response pattern. And you can also have univariate and bivariate frequency. You can look at it in the same way. But here, because it's longitudinal, it makes sense to look at the response patterns. So if we look at the one that has the largest not necessarily the largest standardized residual, because number 1 has larger, but a large standardized residual and several people who had that response pattern. So 24 people had 1, 0, 0, 0. But the model, as specified, estimated that only 13 people had that pattern. So here is misfit. And we want to understand that misfit. And so I'll show you how Tech 10 can help us understand that. Okay, so let's explain what this table is. So we have illness 1 and illness 2. So that's measurements at time 1 and time 2. And then category 1, so if you think of a bivariate frequency table, so you have 1, 1, 1, 2, 2, 1, 2, 2. So it's the 4 cells of the frequency table. So the cell what we notice then in the last column where we have standardized residuals is that category 2, 1, or this would be value 1 and value 0. So 1, 0, that cell has a standardized residual of 4.103. So this is time points 1 and 2, 1, 0. So we have a large residual there. And so the question we might ask ourselves is, for that same, what happens if we go on and look at time point 1 and 4, but still 1, 0? The same thing. And it doesn't look like it's a problem when it's between 1 and 4. It's only, the problem is between 1 and 2. And if we go on, we can then look, whoops, I went too far. Then we can look at 1 and 6, the same thing, and that doesn't look like a problem. And anyway, you can go on looking at all kinds of issues. But what we can see is that there's something wrong between the 1 and 0. There's some problem there going from 1 at time 1 and 0 at time 2. And there's something fishy about response pattern 1, 0, 0, 0, and the fishiness seems to be in the 1, 0 part. And so then that makes you, think back about the data collection, what happened, particularly at that second time point. What about a person who was ill at the first time point and then, was never indicating illness again? So that might be a pattern that is odd. So TEC10 is a really good tool when you have categorical outcomes to help you better understand the misfit of your model. And you can understand it by looking at univariate frequencies, bivariate frequencies, or response patterns. So it's quite a useful tool. Okay, so I'm going to skip now to slide 207, where we're actually going to estimate the growth model and talk about that. So that was just an aside for assessing model misfit. So here we're using the maximum likelihood estimator. We've got the categorical option, which we talked about. An alternative is the WLSMV estimator. And as I said, that would be a probit regression model. And we talked about the growth model briefly. Our time scores are non-equidistant, 0, 1, 3, and 5. And we've regressed our intercept and slope growth factors on drug, which is a treatment variable. So looking at our results, because we're in the categorical outcome maximum likelihood framework, we get a log likelihood and information criteria, but we don't get the traditional fit statistics. So then what are we most interested in here? We want to see, so ion drug should not be significantly, there should not be a significant effect because we had randomization. So that confirms that there's no treatment control difference, so I guess the randomization was okay. What we're interested in is S on drug, because we want to know whether the drug had an effect on the progression of the development as far as the treatment went. So we see that there's a negative significant effect. So that means that over time, the illness decreased for the treatment group, and that's what we would want to see. And just to remind ourselves, we have the, you can see that the thresholds are held equal. That's parameterization 2. Now, we're not showing the means, but this is a conditional model, so means wouldn't have been estimated. But you can, if you looked at TEC 4, the mean of I would be 0. Here are some further readings for you on this topic. And I thought I guess we had the picture at the beginning. Yes. So at the beginning, we had the picture which showed that the treatment group went down over time and the placebo group, or the control group, it went down. But obviously, when we did the regression of S on the treatment, it answered the question that that was a significant difference there at the end. Oh, thank you. So,
and just to
S on drug tests that effect.
Just to add to that, so here we have an example of a negative slope and a negative effect on the slope. So the way you can start thinking about this to disentangle it is look at the intercept of S. The intercept of S is regressed on drug, so the intercept of S is the mean of the slope for the placebo group. So that is negative. Now then you regress S on drug, and that effect is negative, which says that when you're in the treatment group, the negative slope is even bigger, negative. So it's the sum of these two negatives creating this one. So that's a negative effect on something that's negative. If this was a positive effect on something that was negative, then that would mean that we would be totally confused. No, we would mean that this would go up instead of down. Anyway, so
Well,
I
we
think
should take questions.
that's a perfect timing.
And I just wanted to say, so at 5 to 5, if we're still taking questions, we will shut down our computer and we will go out and we will take questions from people or talk to people outside so that they have the room empty. So if you see us at 5 to 5, start shutting down our computer, don't despair, just wait for us out there. We'll be out as quick as we can.
Nothing personal if we start fiddling with our computer.
Exactly.
All right, questions? Yes.
Repeat the question.
STDYX, it's...
Oh, that's old output.
It's an old output. It means it's standardized with respect to both the eye and the drug. And in this case, you would not choose that because you don't want to standardize with respect to a dichotomous X variable. Which reminds me of another thing to stress. When you have this categorical R, remember that you only declare dependent variables as categorical. So, for instance, you don't say categorical equals drug, because drug is an X variable. It's just a dependent variable that you want to influence or say something about, so that you go from linear regression to logistic regression.
Okay. Yes.
Going back to parallel processes, what's wrong when subgroups are correlated at greater than 1?
Could you give us a slide number?
Just in general.
So in general, I think I know the question. I think in general, the question is when some of the growth factors correlate greater than 1, what does that mean in a parallel process model? That can be because you need to include residual covariances, correlate the residuals of the two, of the 2 time points, of the 2 processes at the same time point. So can you make this thing? Right. So it may say you need that. So you could try that.
You're trying to channel too much of the correlation between MAT7 and AT7 through the growth factors, so that they correlate 1, and this becomes a non-positive definite matrix. So you need to probably channel some of the correlation through there. More questions? Yes?
Slide 163.
163.
Just had a question in the model. You say the I at 0 S, the next line down.
Right.
It's overwritten, and then could you just explain that again?
Yes. Because we have the parameterization where, so the default, because this is continuous, is for the parameterization where the intercepts are 0 and I and S are free. However, Bengt wanted to use the second parameterization where the intercepts are equal and the mean of I is at 0 and the mean of S is free. But he had to state those specifically to overwrite the growth modeling defaults. Because the default for continuous is to use parameterization 1. So Bengt wanted to use parameterization 2. So he had to override them by specifically specifying the equality of the intercepts and the mean at 0.
So the program reads the lines. Here it sets up the default, and then it sees we want to change it 2 ways.
Over here?
You point.
You do
Okay,
it.
a gentleman in a bluish shirt.
Question on slide 191.
191.
Yeah, you center on time C. Is that simply to reduce collinearity when you choose some middle range value of C?
Yes, exactly. To reduce collinearity between the linear and the quadratic variables, you would want to choose, say, the average time. That's one way of doing it when time is a variable. It doesn't hurt as much, this collinearity, when time is a parameter. It's just parameters get highly correlated, but it certainly doesn't crash it. Yes?
For the last example,
Yeah?
when you have values compare the AIC or BIC, the second model seems worse than the first model.
There is only one model here in this example.
Last two, yeah, this one.
Yeah.
When you don't have the graph,
Right.
one of the factors, the AIC is smaller.
Yeah, no, it's actually here. In the first example here, the first version, first analysis was for the treatment group only. Now you have treatment and drug group, so it's a different sample size. So you shouldn't interpret the differences there. Yes.
On slide 168, when you are comparing the effect of the interaction, where do you find the standard deviation for each of those variables? Is that in a text output?
Standard deviation to standardize for math courses, you get it from type equals basic. Standard deviation for I is the square root of the variance that you estimate. That's printed in the model output.
Okay, and what about you drop E? Should that be the residual variance from the output?
Yeah, I dropped E here because I only focus on the systematic part. Yes.
So when you're interpreting interactions,
Yeah, you can just drop it. Yeah, you're only interpreting the systematic part. Yes. Mm-hmm. Yes, gentleman there.
Back to slide 176.
176. They like that, Linda.
Rather than having the residuals correlated between SM and SA, could you have, let's say, for example, SA regress on SM?
So the question is, can we do regression instead of correlations here? I think what you might want to do is regress SM on IM and SA on IA, but you can also regress SM on IA and SA on IM. That you have the time ordering that these two happen at grade 7 and slope happens thereafter. So the arrow can go from here to there, from here and there. That would be relevant in this case and probably would be making the interpretation easier than looking at these residual covariances. Yes, lady in the far back. Could you? Sequential processes? Okay, you want to say something about sequential processes?
Well, you would set it up pretty much just the same as the parallel process model as far as the input language goes. It's just that in your path diagram, one would follow the other, and then you wouldn't want to be, you would want to be regressing the later sequence growth factors on the earlier ones, but not, you want to keep that time sequence. So it's pretty much the same thing. It's just pulling one out, and then since these things don't happen at the same time, you wouldn't want to be relating them to each other. You would want to be relating later growth factors to earlier growth factors as far as a regression.
So just to emphasize, so if attitude were later sequence of events, you would put that in columns to the right of these 4 columns in the data, and have a growth model for the first part, growth model for the second, and the relationship between the growth factors. And we have an example of that in August last day. Yes?
On page 207 again.
207.
So you're not identifying independent variables as categorical. If say, for example, if there had been 3 levels of the drug, so you had placebo, drug 1, and drug 2, would that change anything?
The question is, how do you deal with a 3-category nominal X variable?
Well, you would do that just like in regular regression. You would have to create 2 dummy variables from those 3 categories. So that's how you would do it.
Mplus does not do that automatically at this point, so you have to do it yourself. Yeah.
Over here? Okay.
Just for clarification on slide 209, did you say that the S on drug tested that the difference between the 2 groups at that last time point, that I guess for the picture of one on 194?
No, that's one interest that you could have, but no, it doesn't test this difference. S1 on drug tests that the slope is different, that the decline is different. You could also develop a test of whether they're different at the last time point, based on the estimated growth model. Thanks. Yes?
Can you just go one more time, the negative slope and the
So if I have a predictor, like in mom's ad, predicting that attitude slope, so what does that mean if it's mom's ad is a positive beta or a negative beta in terms of substituting?
Yes. So the question is about, say that this is math attitudes, and then we have mother's education having a positive influence on that slope, which is generally negative. Then that means for those with high mother's education, the slope is less negative. It can even be to the point that it becomes positive, but it turns this way. The clock arm hand turns this way. If the influence is negative, the hand of the clock goes this way. So I think about it. You could sort of evaluate the mean of the slope at different values of the covariate. Then it becomes very clear. Okay. You can do more. We can be here for it. We have at least 5 minutes left.
Well,
think of a
then
question. Yes, the
okay.
question's coming up there. Page 207. That looks like we can tell which ones are popular, Linda, or very unclear.
It's just an input. So, what's the question?
What was the last part? Yeah, we have a bracket here, yes. And it gets an exclamation mark,
right,
which means it's a good move.
That just comments that out.
Hmm?
No. Oh, the dollar. All right. So are you talking about this last line? No,
this line?
Okay. So
Good,
as we said, when we have categorical outcomes, we don't talk about means anymore. We talk about thresholds. And a categorical outcome can have more than 2 categories. So that means if they have 3 categories, they have 2 thresholds. And we needed a way to refer to the thresholds. So it's the variable name with a $sign and the threshold number. So if that variable was 3 categories, it would also have illness 1, $2 to refer to the second threshold. So it refers to thresholds.
So in the binary case, as we were concerned with here, it's the counterpart to an intercept. It's actually the negative of an intercept. But it plays the same role as an intercept. We want to hold it equal across time to emphasize the measurement invariance assumption. What was your name again?
The estimator of ML for categorical data, is that now to be considered something that one first does, or?
The question is, which estimator should one really use as a first stab at this? What do you think, Linda?
Well, I'm very fond of probit regression over logistics, so I would probably go with WLSMV.
But you could do probit in ML with link equals probit.
But in WLSMV, I think people are happier when they get their fit statistics.
So if
I'm not saying that's a good thing, but I'm just saying.
So if we came up with an ML fit statistic for overall model fit for categorical, you'd be even happier?
No, because I like WLSMV.
Thank you. Otherwise, we would have done it. Okay.
But I mean, I like the probit model better. I mean, for those of you who were here for topic 2, you see that the probit model is, I think, more flexible. And so I like it better. But logistic regression is so overwhelmingly popular everywhere that sometimes you have to do logistic regression, or you would be going so far from what people do in your field to become a pariah, and you wouldn't want to do that. So you have to take that into account too.
Don't be a pariah.
Yeah.
Yes.
It's not.
Binary variable. What about if you're looking at something like death or FFX that can't change, or once it becomes a 1, it can't change? I assume that you'd want to use some sort of survival analysis.
Yes. Right. If you have a binary variable that's death, what you want to model is time to death. So that's tomorrow.
Okay. So that'll get you to come back.
Or not.
All right. Okay.
All right. Thank you, folks.
If you have questions, wait for us for 5 minutes.
See you tomorrow.